So welcome back, everybody, to the final session of today's dengue side meeting that we've held to celebrate the United Nations General Assembly, the 75th General Assembly. We've had 3 sessions so far: vector control and WASH in the age of COVID, vaccine hesitancy, dengue, and rebuilding trust in the community. And then just now, the session that finished, driving innovation in vector control. All 3 sessions really emphasize the role of community in the approaches taken, whether it's vaccine hesitancy, countering misinformation, filling that vacuum with science as opposed to conspiracy theories, vector control, looking at the way kind of those COVIDized communities, which are now far more aware of public health, infectious diseases, can be kind of used in a far more positive engagement in terms of constructing vaccination programs that actually work, and then innovation from a community-centric approach. What do the people need? How appropriate is it? How sustainable is it? And using that as a set of drivers for driving innovation at a vector control level. We wanted to include this final session simply because, not just because climate change is a very topical thing and it's UNGA, and I'm sure it's being debated, and it was all last week, I know that. Not just because of that, it's simply because of the massive impact it's having on dengue. In 1970, 7 countries were presenting with dengue. Now we've got over 110 countries presenting. Just 2 weeks ago, we've had the first autochthonous cases of dengue in Rome, in Italy. We've had several cases self-generated in France, including at altitude, the Rhone Alps region, not just the southern areas of France. Spain this year has seen the same pattern. We've even had our own journalists go out to Nepal and interview the Ministry of Health earlier in the year, where they had dengue outbreaks, massive outbreak at a very high altitude. So there's a lot going on. A lot of this explosive march of dengue is underpinned by the vector distribution, vector ecology, driven by climate change and allowing Aedes aegypti, Aedes albopictus to colonize new areas. And we wanted to kind of have a look at that from a predictive perspective and also from the virus perspective as well. So I'm very honored and delighted to have Professor from the London School of Hygiene and Tropical Medicine at the Center of Math Modeling on Infectious Diseases, as well as the Center on Climate Change and Planetary Health, a Royal Society Dorothy Hodgkin Fellow, and also Dr. Sadie Ryan from the University of Florida, who's the Associate Professor of Medical Geography, the actual director of the Quantitative Disease Ecology Conservation Lab, the QDEC lab. And so I think without further ado, I'd like to pass over the floor to Rachel, but a round of applause for both of you for a virtual applause for making time for this. I'm going to disappear. There we go. Yeah.
Thank you, Kamran. Thank you very much. And thanks for pretty much giving the introduction to my talk. That was very useful. So I'm going to talk to you today about the thinking we've been doing about how hydrometeorological extremes maybe we can use the understanding of these increased and more intense events and think about how that can be linked in with dengue control and preparedness. So as Kamran pointed out, the distribution of the vector and countries reporting epidemics of infectious diseases has rapidly expanded over the last few decades, in line with dramatic warming of the global temperatures as well. And now it's estimated that around half the world's population is at risk of dengue. And the reason for this expansion is multifaceted, and we have things like international travel, which are allowing people and the vectors to spread the virus to new places. Also, trade, particularly in used tires, has allowed invasive species to be introduced in new places. The climate crisis, so we're seeing very dramatic warming of the temperatures, which is allowing the vectors to expand to higher latitudes and altitudes. And we're also seeing a change in the timing and intensity of extreme climatic events like hurricanes and droughts. And another reason that this vector has been able to spread, and we're seeing these explosive epidemics of dengue, is partly to the way that people are being forced to live in very crowded, overpacked areas without proper access to basic environmental hygiene services. Here we can see, this is an image of one of the largest favelas in Rio de Janeiro. We can see a very sort of densely packed area, and you can see lots of sort of blue dots on the picture, and they are water storage containers, which are relied upon particularly in the absence of a reliable access to the pipe water network. And these can become ideal breeding sites for the Aedes aegypti mosquitoes. So in Brazil, in particular, we're seeing an expansion of dengue, and we can see the traditional barriers to transmission are being gradually eroded. So this is work that's been prepared by Sophie Lee, who's doing her PhD in my group. And we can see here the number of microregions in Brazil which have exceeded an epidemic threshold of 300 cases per 100,000 from 2001 to 2008 in the top left. And we can see the areas in the south, much of the Amazon and some highland areas in the southeast were relatively protected. And then we can see that as we add more years to the database, every few years, the dengue transmission zone is expanding. And we can see, as of last year, it's really reached into the Amazon, previously protected because of its relative remoteness. But we're trying to understand the mechanisms that's allowing the dengue to spread further south and into more remote areas. So as well as warming temperatures, we think this is related to the movement of goods and services and people around this hierarchical urban network in Brazil. And Sophie is analysing this database provided by the Brazilian Institute of Geography and Statistics, which helps us understand how these big metropolises are connected to each other and to smaller places, and to see how over the last decade the transport links have changed. And we can see in the map on the right that we have many more sort of connections from Manaus to the rest of the Amazon. So before, dengue was pretty much limited to these hubs that were connected by air to the big urban centres, but now we're seeing many more roads and other things being built in the Amazon, and that is having a big impact on the spread of arboviruses in that region. And I'm particularly interested in how things like droughts can exacerbate dengue outbreaks. So following on from some work that we did in Barbados, we found a very interesting relationship where drought conditions followed by warm and wet conditions seem to lead to an increased risk of dengue outbreaks. And using information, if we're using indicators that monitor drought, we can use those to predict the risk of dengue around 5 to 6 months in advance. So this is a very interesting finding that we had for a small and developing state, and we wanted to test this for a larger geographical region. So we're now having a look at this across Brazil, which has a whole range of different climatic and urbanization situation. And we can see that the incidence of dengue, here we're looking at, on the left, we're seeing how dengue, intraannual variability and seasonality in dengue in the 27 different states of Brazil, and how that's varied over the last 17 years. And we can also, on the right, compare that to the drought indicator, where the brown areas are indicating drought periods, and we can see that particularly in the north-northeast, these droughts are becoming more intense and long-lasting. So we've been thinking about how the levels of urbanization and how access to pipe water might interact with these hydrometeorological extremes. So the map on the left here is just showing the proportion of residents living in urban areas. So we can see that particularly in the northeast and the Amazon region, we see more sort of rural areas. And this correlates very well at the microregion level to access to pipe water. So we explored using a modeling technique where we're using a Bayesian hierarchical model with distributed lag nonlinear models embedded within that. And here we're exploring how this drought severity index interacts with the socioeconomic conditions, so be that urban areas versus rural areas, which correlates with having higher or lower access to the pipe water network. And we can see that in both urban and rural areas, we seem to have, with extremely wet conditions, we have an increased risk at very short lags, which is what we would expect and coincides with the literature. And then we can see, particularly in rural areas, again, we see this delayed impact of drought, which 5 months later is followed by an increased risk of dengue. So this kind of information is very useful for policymakers thinking about the different timeframes in which climate forecasts could help us intervene and make sure that particularly those areas which are not well serviced having access to proper vector control, and there's awareness about keeping mosquito breeding sites clear. So how could we link this kind of early warning information to early action? Well, in 2014, we put together a framework where we were using real-time seasonal climate forecasts from the Brazilian Climate Center CPTEC, and combining this with the latest cases of dengue in the Ministry of Health, and combining this all together to make probabilistic forecasts with a 3-month lead time. And we'd like to expand on that framework and particularly focus on those areas where we know that seasonal climate forecasts have more skill. And that tends to happen during El Nino and La Nina events. And during El Nino events, we do seem to experience more intense drought conditions, particularly in the Amazon region, and also warmer conditions. And we can explore where these models seem to work best and seize those windows of opportunity when our seasonal climate forecasts of dengue are likely to be more accurate. And we're exploring ways to iteratively update our forecasts as we approach a target. So if we're interested in forecasting dengue in the month of March, for example, in the southeast of Brazil, when that peaks, we can start using forecasts of the drought conditions, of the temperature, 6 months in advance. And as we approach that target, we can start bringing in observed climate information and improving and in reducing our uncertainty as we get closer to the point which the policymakers would like to prepare for. And we've been working with Dr. Felipe Colon in our group at London School of Hygiene and Tropical Medicine to try and implement some real-time operational frameworks. So we've been doing a lot of work in Vietnam. And here I'm showing an example of a platform that we've been developing for Paraguay, which provides information using the real-time dengue information and also seasonal climate forecasts, particularly from the ECMWF and other models that are available on the Copernicus data store. And we're using those in a real-time framework to make monthly predictions up to 6 months in advance, and also providing verification information to give an idea of how well this model may have behaved in the past. And of course, going forward, our dengue control efforts will be very much impacted by the COVID-19 pandemic. We recently published an opinion piece in the BMJ about the sort of syndemic scenario and the combination of COVID-19 with epidemics of many other neglected tropical diseases, including dengue. And we recently published with colleagues at the Global Vector Hub at the London School of Hygiene and Tropical Medicine and other policymakers some recommendations of maintaining global vector control efforts amid the COVID-19 pandemic. And I think it's very important for us to have a World Dengue Day. We know that dengue is a neglected disease, it's a climate-sensitive disease, and these climate extremes are interacting with socioeconomic vulnerabilities, which are leading to very unpredictable, explosive, and damaging epidemics. And we think it's very important that dengue is very high up on the climate change and health agenda. And thank you very much for your attention, and I'll welcome any questions.
Thank you very much for that, Rachel. Fascinating. There's a couple of slides, all of it was fascinating, but a couple of slides about drought exacerbating the dengue outbreaks was very interesting. Somebody was actually asking a question in the box on the right. They're asking about droughts and this kind of thing. So I'll wait until the end of the session to put questions forward. But thank you very much. And I'll just have to say that thank you very much for mentioning the World Dengue Day at the end as well. We're very proud to have you on board in terms of our dengue advisory group, and all the DAG members today have really put that forward, the importance of having a focal point, a World Dengue Day, and that's what we've been campaigning for, so we really appreciate that. Thank you very much for that. I'm going to quickly switch to the second speaker, if that's okay. So thank you, Rachel, for that, and we'll bring you back in at the end of for the Q&A. So Dr. Sadie Ryan, the Associate Professor for Medical Geography, University of Florida, and Director of the Quantitative Disease Ecology and Conservation Lab. I'm just going to, I'll hand the floor over to you, Sadie, and I'm going to turn myself off. So over to you.
Thank you so much, and thank you so much for this invite. This is a wonderful forum for thinking about this stuff, and it's a very nice juxtaposition with what Dr. Lowe just described, because the stuff that I've been working on is much sort of bigger scaled and longer term looking, and it's really interesting that the decisions that people make tend to be somewhere between these scales. And so I'm here today to tell you a bit about sort of aligning climate change prediction models that we do with planning frameworks and seeing if we can get to that. Slides. Okay, so I hate to give you biology lessons late in the day, but we're going to do a quick introduction to a physiological model for malaria. Now you're saying, Sadie, this is about dengue, but we started with malaria with this work, and we mapped sort of what we thought were pretty straightforward things. I'll then talk about Aedes transmitted disease models, because there's 2 vectors involved with this, and the fact that we shifted into a different framework for thinking about this and how that affected how we can communicate the results of these kinds of models. And I'll talk a bit about vector-borne diseases and climate change models and decision-making. And then I want to sort of open it up to some summary thoughts on the utility and purpose of these kinds of mapping approaches. So we take a malaria model for transmission. R0 is basically your onward transmission rate. Its real definition is the number of secondary infections caused by a single infection dropped into a naive population. When we think about this for malaria, it's a bit more complicated because we have a mosquito involved as well as a human. But what we see here is that cycle of mosquito sucking up the pathogen, much like they do with dengue, and then it develops within that mosquito, and then they're injecting it back into the next human host. What we also notice about this is much of that process in the mosquito is taking place outside the human. So that means they're subject to environmental temperature. And so when we take this classic McDonald equation for the transmission of malaria, we see that many of the rates that go into this are about the mosquito and the pathogen, and that many of them are temperature sensitive. This allows us to think about what are temperature sensitive rates. And so here's a sort of diagram of that idea where we have a performance curve with temperature on the bottom and the rate of a performance going up on the side. And if you want to sort of take that less abstract, we could think of that as fighting rates, egg laying rates, so oviposition, survival, those sorts of rates that guide the life history of both the mosquito and the pathogen. And if you think about it, we're all just bags of chemicals. And so chemical processes, as they speed up, it's these chemical reactions that take place that guide the enzymes and the kinematics inside our bodies. As these speed up with temperature, they reach this optimum process where they're going as best as they can. They're absolutely optimized. And then it breaks down pretty rapidly above that optimum. And so there's this maximum temperature, basically things are getting cooked, beyond which things do not happen. And so we have a minimum temperature and a maximum temperature that's bounding that, but we have this sort of right-shaped curve effect. And to put this into context of why on earth am I talking about this with mosquitoes, previously people measured this and accounted for this with a linear shaped function. And they probably weren't wrong over the space in which you observe most often these temperature processes taking place. So it's not that people were specifically wrong, it's that they weren't thinking about how that process then gets back into an equation to describe this. So because these equations describe processes that both go one way and the other with respect to temperature, if you put the linear responses in a curve, you still get a curve for optimal temperature of transmission. However, because those processes are continuing on to impossible levels, it's probably shifted over. And so we wanted to see if that was true. So we decided to take these rates of mosquitoes in the processes for this transmission model and fit that with data taken from empirical studies in the lab held at constant temperatures. And we fit them with different shapes of equations, so symmetric and asymmetric curves and linear, just for comparison to see what best fit. Then we wanted to calculate an R0 optimal temperature as a function of temperature, and then we wanted to validate that with field data. So for malaria, we found those rates, and they were all curved in one way or another. They're not all the same looking curve. There weren't that many data. That's a really important point, that it's kind of sparse data. But we were able to find these lab-based studies for all of these. And we put them back into this R0 versus temperature model. And we found an optimal temperature for malaria transmission of about 25 degrees Celsius. The previous estimate was a good 6 degrees hotter than that. And so we wanted to know, does this validate in the field? So we took 40 years worth of field transmission studies, so that's the entomological inoculation rate, placed each of those on the month temperature at that location using the ERA 40 project, and projected those dots onto this map. And so what we see is that the new estimate for the R0 temperature curve really captured those field-based validation studies. So we felt pretty comfortable with that. We published it. And in these keywords, you see the word climate change, but we didn't really get into climate change yet when we first published these curves. And so the question of sort of how do we tell people more about this is, people like maps. And so I simply took these curves that we had and I cut them into quantiles and said that the top was the most optimal quantile, and then projected it onto maps using very large scale climate data. So this is what was available. This was World Clim data, and it's aggregated mean monthly temperatures at a 10 kilometer squared scale, roughly at the equator. In order to describe where they can't be in terms of moisture, we used an aridity mask derived from vegetation data from remote sensing. And that basically takes away those areas that are just too arid for the mosquito life cycle to start. And we have what we call a Goldilocks scale on the side, where dark red is too hot, dark blue is too cold. And as you can see, this picks up quite well the patterns that we sort of intuitively think about in Africa on the ground. We also looked at this in context of top-down modeling, where people were looking at actual prevalence data, and we found it really aligned nicely. When we look at that old temperature model on a map of Africa, it predicts that most of the continent is too cold for malaria most of the time. And so maps provide us with this nice way to visualize what we're doing with our models. We can also warm these up using climate change scenarios. Again, this is still malaria. We can plot this as a function of population density and that temperature suitability, so saying what bounds on the physiological temperature of transmission exists for how much of the year. We scaled that to 1, multiplied it by population density, and you see this density hotspot of risk marching across the continent as we move through the century. So let's get to dengue, right? So when we made these maps, people really picked up on this. And so clearly maps are a useful tool for communication, but it's important to know what they're communicating and to be able to really describe that well as a scientist who wants to be working with the applied. So we went to dengue, we did the same thing, pulled data out of the literature, fit the curves, validated it with field data, and this time we had 2 vectors. So we have Aedes aegypti and Aedes albopictus. We discovered that Aedes aegypti is a bit hotter than Aedes albopictus in its optimal temperature. And what we had was human case data of 3 arboviral diseases having outbreaks simultaneously. So we were using human case data as our validation in these cases. We had also moved into a different way of fitting these parameters. So we were using Bayesian estimates which means that we had a different way of describing what we could map. So what we have here is the posterior probability at a greater than 97.5 percentile, for where R naught is greater than 0. So this is saying it is capable of starting, right? So this is sort of suitability transmission at these very nice, tight credibility intervals. And so on this map, which we published with the first paper, I used a color scale to demonstrate how many months of the year these locations were suitable for dengue transmission in each of these vectors. You'll see on the top right, I've put their curves again, so you can see that Aedes aegypti is the dark blue, the hotter one, and Aedes albopictus is the paler blue, the slightly cooler one. And we can see those reflected in South America nicely. We sort of see that that's reflected in these current temperature mean maps. So then we wanted to take this bigger, right? So we said, what is this going to look like in the future, and what is it going to look like at that global scale? And so this is looking at the top panels are Aedes aegypti on the left, Aedes albopictus on the right, remember hotter, cooler. And then we have our lower RCP of 2.6 that I hear nobody bothers doing anymore in 2050, and our business as usual or worst RCP of 8.5 on the bottom. And what we see here is we're beginning to see a pattern where Aedes aegypti can expand towards the poles and get more intense in those colors. That's the number of months per year that it is suitable. So those pixels are within that temperature range for that many months of the year. Whereas Aedes albopictus starts to break up in the tropics. And if you look at Australia, that's a really nice place to look to compare between the maps. As I said, maps are pretty, but maybe they're not the best way to communicate really local things. And so we start to see that we're seeing these different patterns between the two vectors, even with the same pathogen. And that means that we need to think differently about those two vectors when we're thinking about sort of how to plan and anticipate for this. And so one important thing about the ecology of Aedes mosquitoes is they're not anopheles, right? So anopheles are our malaria mosquitoes. Aedes are a container breeder. They have urban risk potential. And in many of these cases, we see that it's about people, not precipitation. And Dr. Lowe alluded to this, that because they're container breeders, a lot of times it's about where people are and what they're doing when we get down to that local level. And in fact, this study that I'm showing here, in 2013, Dr. Stuart E. Bauer and team, including me, we looked at what happens if you compare a neighborhood where there's reliable water, there's air conditioning, people can close their windows, and a peripheral area where the housing quality is a bit lower, and people use a lot of water storage because they don't have reliable piped water. And what we found in the central area was we were able to pick up a rainfall signal in emergence of Aedes mosquitoes, whereas in the peripheral area, that rainfall signal disappeared because people's behavior swamped the signal. And so this is a really interesting thing to think about when we try to describe how these thermal suitability maps translate into risk. And so what we did is we simply said, where are people, right? Where are these people at risk? And for how many months of the year are how many people across the globe falling into those suitability categories? And so we see that up to 6 billion people are currently at risk of at least 1 month of the year being suitable for transmission with Aedes aegypti. Now, does that mean that all those people are going to get it? No. 1 month of the year is very low suitability. But this starts to break out where we think we might want to start focusing our interests in anticipating potential future outbreaks or anticipating where it might be becoming more endemic. And I think that this is slightly different than static maps of suitable or not suitable. And so I think we're beginning to see some sort of temporal utility in this. We also then took future scenarios. And what you see on the left is any transmission, so this is 1 or more months, and on the right is year-round transmission. These are very different things to plan for with public health and with intervention ideas. And so what we see on the top set of these two quads is 2050 scenarios, on the bottom is 2080 scenarios. In each one, Aedes aegypti is on the left, the hotter one. The cooler one, Aedes albopictus, is on the right. And what we're showing is the difference from now in people at risk under climate change. Marching across the bottom are the different representative concentration pathways. So technically going from better to worse, with the exception of the two in the middle do something slightly different if you look at where they start to mitigate. And so that makes for different patterns. the boxes represent different models of climate. So these are the different global circulation models put out by different centers. So as you can see, the boxes represent kind of the range by using different kinds of models, while the RCPs tell us what happens with the different mitigation pathways or lack of mitigation pathways. I think the nice take home from this is that we see that things are getting too hot for Aedes albopictus in some populations in some parts of the world as we march through these climate change scenarios. Whereas for Aedes aegypti, it's always going to be an increase in people in those risky categories. So what do you do with that? One thing we did with this paper that we felt was actually beginning to speak to questions about how you make decisions was we aligned this with the Global Burdens of Disease Regions approach. So we broke those maps out into regional impacts. And this is a table full of numbers, which is a little alarming, right? But if you think about what we might want to think about, regions in this table have been ranked based on the millions of people exposed for the first time to any transmission risk. And so that's telling you how many new people will be exposed. In the parentheses, however, we have that net change. That's simply the first people to be exposed minus all the people who are no longer going to be exposed. And so when we think about first exposure and net change, as those things we're looking at, those are slightly different impacts to be working with. We see that for the two different vectors, we get a different set of top 10 ordering. And so breaking it out into a table is not that exciting for academic journals. It is incredibly exciting for decision makers because it starts to give us these regional views of what's going on with these maps of risk. And so I think that in some ways we need to have this renewed look at dengue as we're thinking about climate change and as we're thinking about how these maps help us with planning. So this is sort of a longer term tool than the work that Dr. Lowe described. This is thinking about, sort of decades into the future and what we can anticipate as shifts across landscapes. And so we recently put out this map in a paper saying malaria is going to shift across the African continent, right? Because the temperature is predicted for that suitability to kind of move across. However, with dengue, we're going to see this kind of expansion of where population density and temperature suitability combine. And this little graph on the right that you can sort of see from there is actual data from Kenya taken over 4 years looking at causes of febrile illness. And in hotter times, more of the febrile illness was not malaria. It was in fact possibly dengue, possibly other arboviruses. Whereas in those cooler times that fit under that malaria temperature curve, they were malaria cases. And so it may be that we're already seeing these effects in places where we don't think of dengue. And so that's the really key sort of message here is, if we need things like World Dengue Day, because a lot of the decision frameworks are based on malaria in the places where we're now starting to look and reflect on this and say, hey, things might be changing with climate change. So we felt that we'd sort of begun to get to the point of translating maps into these actionable risk for policy decision frameworks. Newspapers were able to pick our messages up in ways that made more sense, even though they were sensationalist. We need to sort of move away from that a little bit into the more practical. But so the big question here is, what about scaling down? And that's where we sort of bumped into some issues. So Dr. Lowe mentioned our work in the Caribbean. For this, an entirely different set of spatial models works because we're talking about very small spaces. We have data, and we're lucky that there are data-rich sources here. But really the question is at a sub-island level in neighborhoods, and where do you have sort of high-intensity hotspots? But we had been asked to use these global maps that other people had put together, these niche maps, and to sort of say how well do those scale down? And we found that the data that goes into them is very, very sparse, these sort of global data sets. The geolocations don't always seem to be accurate. Some of these mosquitoes were swimming, if you look at the bottom left. And the scale at which these pixels exist on these maps are big, right? They're not necessarily practical for planning. And the information, as I mentioned before, the sort of temporal utility of something that says, yes, it's suitable or no, it isn't, doesn't really scale with where you would then allocate resources. And so it's important to think about sort of where we want to use which kinds of model approaches and at what scales be they maps or forecasting tools or both, right? These spatiotemporal approaches. I mentioned before that we have these sort of city-level social ecological systems of vector-borne diseases. Consistently in our studies in Ecuador, we find that water supply is really important. And so this is more about people's behavior and water supply than it is about capturing a precipitation signal. But somewhere in between that seems to work for different landscapes. And so that's something we're still puzzling through. And so when we think about global maps, you know, we can say, okay, we just made these sort of global scale questions. And so we have this issue of, you know, is there data uncertainty at smaller scales just because what we did was create a global scale map? Is there also data uncertainty generated when we scale up these models? Possibly. We also know that there's data uncertainty in the climate models that we can use at these scales. And so we need to figure out how to sort of capture that and explain it before we use this kind of mapping approach to make decisions. Intervention, specifically for dengue, tends to be local-ish. So you think about spraying, you think about tipping out containers, think about thinking about vaccination programs. But policy and planning tends to exist more at the regional scale. And so maps at these kind of mesoscales may matter more for thinking about these decisions. And so the question is, do those then reflect the kinds of decisions that can be implemented at the intervention level? And this, I think, is sort of a really important thing to think about when you're engaging with actual applied. So this sort of takes it out of the academic nice modeling and puts it back into the applied questions. And so when we think about this, I've mostly worked with agencies talking about malaria planning at large scales. And so what are the decisions that can be made using these large scale global regional maps with these longer term climate projections of sort of mean events in the future? We can target on-the-ground surveillance and responses to changing epidemiology. If we know that there are going to be shifts, can we get out ahead of that? And can we know to anticipate it? We can improve a country's capacity for collecting and using information at the national level. So if you want to know about subnational information, you need to then bring it up to the national level so that it's at the decision-making level for that country. We always need to be building capacity in health systems, but using these projection maps, we can think about what kind of health system changes we're going to need to build capacity for. In terms of aid agencies, thinking about how to refine the country selection and strategic budgeting for international programs can be informed by these large-scale, longer-term models, as they can help with the first view of anticipating where to come from. Importantly, and this is something I really value in my own work, is developing regional approaches and partnerships. I think it's much more useful for me to develop tools for someone else to use or to help translate what the heck we've done into something actionable than it is for me to come and tell someone what to do. And so I think that sort of plays into the importance of today's discussions and thinking about sort of the utility of the kinds of work that we do. So with that, I'll thank you and obviously thank a bunch of funders.
Thank you very much for that, Dr. Ryan. That was a fantastic talk, full of a lot of information to unpack there. I'm not just talking about the findings of your published work just now, but at the end, the impact, what really struck me was the impact, potential impact to governments in terms of their predictive capability, strategic budgeting, just their preparedness towards dengue as an example, or any other disease. And Rachel, in terms of your system already being used at the Vietnamese CDC level in terms of predictive tool, what I wanted to ask, and this is the question I wanted to ask, how do you move from those models, theoretical models, into a place where you've got to sign off from a policymaker in government? What are the steps that you need to go through? And are they is it more challenging time now, given where we are with the way climate is perceived out there in governments at the moment? What are the kind of steps? Is it a communication challenge? I'll ask Rachel first, because you have something with the Vietnamese CDC, and give Sadie a breather for a second as well. Right,
I'd just like to say thank you, Sadie. That was such a brilliant talk. I really enjoyed that. Thanks. So yeah, I think that the most important thing is it's really about starting sort of the co-design of these things from the very beginning with stakeholders and the people who actually want this information, want to use it. And it's really important that the stakeholder feels that this kind of climate information will help them, and it's very apparent. So our colleagues in Vietnam have been providing us, well, first of all, they gave us very useful input to help design the system, and you always have to arrive at some sort of compromise between what it would be useful to actually act on the ground and what models and climate information can provide, and making sure you properly communicate the uncertainties in that data. And you have issues to do with scale, to do with lead time. But once you sort of arrive at this sort of this space where you can provide something useful, it's very much an iterative process. So sort of, you know, mocking up either some maps, some communications, seeing if that helps, and then sort of this sort of iterative co-design process, I think, is really important. And I mean, particularly as well, Sadie and I have been working with our partners in the Caribbean, and it's been a very rewarding experience because you can very much feel the difference that the climate is having. It's changing the epidemiology of dengue, climate change, and, you know, through our interaction, our collaborations, you know, adjustments are being made, or our partners are consulting the sort of climate and health bulletins that are coming out to link climate information to decision making. So it's been, I think it's very much about sort of co-design and keeping the conversation going.
Thank you for that. Sadie, Dr. Ryan, would you like to add anything to that? You're talking more about tool sets and the application of those in a longer term view. What would you add to that?
So I think there's sort of, you know, at the two scales, you have these options to do things like early warning systems and forecasting models. And then in terms of these sort of broader scale planning, you know, you can think about these static future event climate scenarios like I presented. And I think one of the things that was, you know, Dr. Lowe talked about our work in the Caribbean, one thing we did was at PAHO, we sat down in a room with vector control, with the Ministry of Health, and, you know, with people actually on the ground doing entomological surveillance, including the people who actually put the data into the computer, because that was really important. And we just sort of gamed out some scenarios and said, you know, would it be useful to know if next year's a high dengue year? Would it be useful to know if in 3 months there's going to be a lot of Aedes aegypti? Would it be more useful to know which neighborhoods are going to be, you know, sort of sparking things? Or would it be more useful to know whether you need more hospital beds? You know, sort of, and what time of year do you make which decisions? So, you know, do you prepare an annual budget? Can you suddenly mobilize your spray team to go from one end of the island to the other if you got these sort of early lead indicators that you were going to have lots of new Aedes aegypti popping up? And so actually asking these questions about sort of what decisions can you make, not simply here's some decisions to make, is really important. And that sort of engagement from the get-go. But it's hard to sort of get on the radar of people who make those decisions if there's not these larger scale questions that have already been, you know, sort of raised, and particularly at the agency level, because they're the ones who say, okay, we're the development agency, we would like to put in a project in this country because they're having, you know, a bad year, and we've decided here are these experts, they made these maps, you know. It's sort of, it's this very interesting interaction, and I put a lot of weight on demystifying the science as much as possible to decision makers. And, you know, Dr. Lowe touched on this question as well, that there's always uncertainty in these models. Yeah. And you have to think about, when does that matter most and to whom?
Great answers. In terms of that, building on those two answers, what kind of collaborations, data collaborations, perhaps tools you might need yourself, would you like to see kind of developed to get you to that point, or to further kind of refine your work? Would there be any collaborations around data, or you know, tool sets that you would use yourselves that would be useful?
Yeah, I think for informing and operating any sort of real-time early warning system, the data is really fundamental. And I think having access to real-time data can be an issue. That there are certain, for example, climate products that are available sort of real-time -5 days, but even depending on the setting or what you're trying to predict, even that can be too long. And the same with the actual disease surveillance data itself. If you want to be providing sort of real-time information, you really need that data up to date. But I do think that the experience with the COVID pandemic and the response has stimulated a little bit more of sort of data sharing, openness, getting those data sets out there. And of course, yeah, it's very important to be able to understand what's happening with the vector, understand what's happening with the land use change. So there are all these different sort of data layers that can help us properly sort of understand and quantify the risks that might be attributable to climate variations.
That's fantastic. Sadie, Dr. Ryan, would you like to add anything to that?
I mean, to echo, obviously we scientists show up and want more data always, right?
Sure.
But in addition to that, I think sort of placing more value on the value of data itself. And, we have epidemiologists who are career epidemiologists who have been filling out forms for 40 years. That is a treasure trove of information, and they should be rewarded for all that effort. And having people who are entomological surveillance, being able to actually talk to epidemiologists is important, and getting the training for how you deal with data and the value of being trained to deal with data and the value of the work to get empirical data, I think needs to be highlighted a bit better. And I think in lots of places where we've had these conversations, it's sort of recognized that actually that's a really good thing. And I think I enjoy it because I think it's becoming more recognized. I think we are moving forward. And I think that's great. And so I think that's sort of, more of what we need. From my perspective, a lot of what people want is they want a hotspot map. They see that we can make these things that look like hotspot maps and they want one, but they often don't know what that is or what they would do with it if they had it. And so I really enjoy having these conversations with people about sort of, as I said, when do you make decisions? What kinds of decisions do you want to make? And then we can talk about which data sets might feed those.
I mean, that is very interesting. Yeah. Perhaps there's a case being built here for a separate communications effort to augment your work and get yourselves into that place with policymakers, like a totally separate communication, not package, but approach to it. But I think it's fascinating. The impacts you've described, both of you, are huge for global health. You can't connect the two things. Everybody should be using this. That's what kind of springs into your head when you read something like this, when you hear this kind of talk, and you wonder yourself, what are the resistors to people not using this at government level? Why are they so reticent? It just kind of makes you think really about what needs to be done to get there. Thank you very much for those answers. I've got some questions from the audience, and I'm just going to filter some of those through. So there is Dr. Cruiser Rachel Vicente, and she's saying, thank you for the excellent presentations. How is the perspective of sustainable transmission of dengue and other arboviruses transmitted by Aedes aegypti in countries in temperate zones with global warming? In these areas, Aedes aegypti can reach the same viability as albopictus for the transmission? Should I? So she's asking, what is the perspective of sustainable transmission for dengue and other arboviruses transmitted by Egyptian countries in temperate zones with undergoing global warming? In these areas.
That's an interesting question that comes up a lot, right? So in our models, we have these two vectors because those are the two main vectors we know of that transmit dengue. And obviously the model is calibrated using lab strains of those vectors and lab strains of dengue in those vectors. So those sort of coupled vector pathogen curves are very specific in those cases. And so whether Aedes aegypti showed up first somewhere and then albopictus, and then there's displacement sometimes. We've heard studies about larval competition between the two vectors making those patterns, or it could simply be when the invasion occurred and therefore the spread, means that you may not have equal viability of Aedes aegypti and of albopictus, even if they are both able to be in that landscape. There might be some competition there. But I don't know quite enough about the entomological specifics to know which of those sort of competitions on landscapes play out and how they play out. And certainly, we know that albopictus is a competent vector. We know that Aedes aegypti is a competent vector. The strains of those two species, when they get to new places, obviously that's gone through a bottleneck. So they may have their own local adaptations that precipitate new competitions between them. So it's a very complicated question, actually.
Yeah, it is a complicated question.
An interesting one.
Yeah, thank you for that. There are Satish Cherukmali from the US. He's asking, are these platforms open source? To Dr. Lowe, he's asking, is your work open source?
Yeah, and certainly the Paraguay example I showed is open source, and we share our code, and if we're allowed to share the data, we do with our publications. So sometimes there are restrictions to sharing data depending on sort of different data agreements from the providers, but we do share all our code.
Okay, thank you. Dr. Ryan?
If anyone wants to play with the mapped model output from the global expansion stuff, it's all sitting on the Harvard Dataverse right now, is the best place it's documented.
Okay.
So we released it all with the paper for every single climate scenario and every simulation model.
Oh, brilliant. So that hopefully answers your question, Satish. We've also got from Rory Gibb. He's saying, thank you to both of you, fantastic talks. He has a question for Dr. Ryan. Do you have a sense of how future evolutionary change, either in mosquitoes or pathogens, could influence these macro scale patterns of risk? For example, through shifting thermal optima for reproduction transmission?
And that is a great question.
Big question.
Over the time scales at which these, my future climate projections are, whether these sort of mean event times, definitely there is scope for adaptation and evolutionary change to occur. And we know that there are local adaptations of mosquitoes to their habitats. And that is definitely something worth thinking about. We also know that, this sort of tight coupling of vector pathogen pairing and the efficiency of transmission when they do find each other, that differs with different pathogen vector combos. And so we will see these sort of evolutionary changes taking place. The thing to think about, though, is that there are these hard limits, right? Those upper bounds really are, systems cannot get cooked. I sort of remind myself that they are actually proteins, and you fry an egg, you can't unfry it. And so I think there's sort of, within those lethal boundaries of the too cold and too hot, I think there is scope for that optimum to shift around a little bit. And I think that we need to get a better compendium of thermal patterns across, different strains in different places, different scales of latitude, and really have a nice deep comparison of that. Again, that requires empirical data. It requires really well-trained entomologists and lab empirical infection entomologists. And so I think we will start to see more of that, because it is an interesting question. Thank you.
It's interesting. Thank you. Thank you for answering that. And here's a question by Stephen Bramier for Dr. Rachel Lowe. In relation to your drought, the thing about droughts, exacerbating in Brazil, dengue outbreaks, so a period of drought and then a lag, and then you can start seeing dengue happening. He's just asking, how are the mosquito populations supported by drought? How do the larvae survive seasons of drought? That's kind of what he's asking. Do you have any information on that? I know you're not coming from an entomological perspective, but that's a question that's popped up.
We think that the mechanism is through the water storage, and so a drought it's like a slow onset hazard, and that will lead to an additional, where there's an absence of reliable water source, that can lead to additional water storage. And it's about this sort of unintended consequence of trying to mitigate the drought and then providing additional breeding sites. And at the moment, the CARFA, the Caribbean Agency for Public Health in the region, are very sort of conscious of these very hot and dry seasons leading into wet and warm seasons, because that seems to be very favourable for having more abundance of mosquitoes during the wet and warm season.
Okay, great answer. Any input onto that, Dr. Ryan? Do you have any input?
I think one thing that always fascinates me with on the colder end of the spectrum is that albopictus have this wonderful thing called diapause. So they can make it through some temperate winters here in ways that are a bit alarming, and it seems they can in fact maintain infection through the winter. And so we're starting to see some interesting things on the colder end as well, you know, as people sort of get in and study this more.
That's fantastic. So I'm just having a look through these questions for a second. So Theodore Sy is asking, are Egypti eggs resistant to desiccation? Does anybody know the answer to that? Well, these are entomological questions, not really climate based, but no, we can come back to Theodore.
They're not completely resistant to it, because we've had some dry out too much to hatch after we ship them.
There you go.
So it is possible they can completely dry out, but they are somewhat, I mean, they can resist some dryness, and then when they get wet again. Yeah.
Okay, good. So just moving out. Yeah, I was going to say, I'm just going to move out of these questions for a second. You mentioned rapid urbanization, both of you did, as a major driver in terms of new breeding sites for Egypti to spread into and colonize. How is your work perceived at this kind of infrastructure development, rapid, the city planners, the kind of the municipal planners, the infrastructure policy people? How's your work? Because that is another series away from the cold face of climate change or disease. One would not necessarily, if you put yourself in their shoes, I doubt if there's the first thing that clicks in their mind, I need a Bayesian map to work out, how I'm going to develop the city slum, integrate it into thing and mosquito proof it. How's your work perceived in those kind of settings? It's a very big impact there. You can have a huge impact in these kind of the way cities are planned and built. How's your work perceived? I'll ask Rachel first. Sorry. Yeah.
Yeah, I think that there's certainly a lot of interest about how climate change might impact upon the urban environment, and very important for sort of city planning in terms of, not only vector control, but also dealing with temperature-related mortality, and, things to do with the unintended consequences of green spaces, and how to avoid unintended consequences of greening cities and providing those additional breeding sites, thinking about, roof gardens. And I think there is a lot of interest to making sure that as we improve our living spaces, we don't then introduce additional breeding sites there too.
Great answer. Yeah. Dr. Ryan, what?
I think one of the messages that we have seen consistently in quite a lot of these studies is that the interrupted water supply leads to people becoming more reliant on water storage. And particularly when you have sort of intermediate access to pipe water, what you tend to do is then store for longer, because you're not always using the water and rinsing out the containers. You're sort of storing for the eventuality that you won't have water coming out the tap. And so that gives a long enough time for mosquitoes to breed. And so we sort of have this, we found it across a few places in Ecuador at this point, and it's echoed in the Brazil work that Dr. Lowe did, that when you start seeing water storage, it's not necessarily when people always use stored water and dump it out, it's when they start to store it. And so I think that has a lot of implications for when municipal planning happens. So sort of thinking about municipal infrastructure, it's not just giving people piped water, it's giving people reliable piped water, right? So it's sort of a slightly extra slice of message. And, you know, you mentioned slums. We're not even talking slums, right? We're talking middle income areas in big cities that are, you know, sort of subject to these different impacts of slightly off infrastructure and slightly older buildings, and, you know, sort of attempts to mitigate different things at different times. And it's that sort of unreliability of municipal services that begins to create things like small mats of nesting habitat for larval Aedes. And so I think there's sort of an interesting intermediate issue there, as well as thinking about sort of just sheer, you know, the process of urbanization and sprawl on landscapes in a large way. So I think we have been heard a few times. I don't know how much that's then led to changes per se. At least in one of the cities we've worked in, they've been switching over from septic tanks to newer infrastructure for water and waste. And I think as part of that, the conversations about how do we make sure this doesn't become mosquito habitat was sort of ongoing while we were doing our studies in the area. So I think it's trickling in some places.
Fantastic. So it's being perceived well. And yeah, so I mean, as we move forward, what do you think the future holds for this approach in terms of mainstream, or, you know, are you optimistic about how this is going to be used? Your work, the impact, and how it's kind of used. I'm asking that because of the huge backdrop of climate denial and denial of all things climate. It is UNGA75 after all, and there's no escaping that reality. So I just wanted to kind of ask you, in your own opinion, the future trajectory of your work. How do you see that navigating all this kind of denial business?
I think it's very valued, and I think we really need to be moving towards a sort of multi-hazard approach. And we can see that things like hurricanes, droughts, these extreme events that are becoming more intense and frequent in certain areas, they can disrupt health in many ways. And it's about trying to leverage those Earth observation, those forecasts, to try and support policymakers in directing, you know, resources to those areas that are most needed, to reaching the most vulnerable populations, and not thinking about just dengue or just malaria, thinking about this whole package of potential negative health impacts from climate change.
A fantastic answer, yeah. Dr. Ryan, would you?
So two sort of prongs of that answer. One is that I've been lucky to be involved in some of these reports and decision making for the USAID Global Atlas Project for malaria, and that's about climate adaptation. And, you know, that was subcontracts money run through my university, and basically they wanted me to rerun the models using their specifically calibrated climate models for specific areas, and to help inform both regional and country level reports across Africa. And that was that sort of really opened my eyes to how this works and how this becomes policy, and what the information is that can be used to trigger decisions. And sort of, you know, it is not my job to put dollar amounts on any of this, but they literally have economic models to talk about different season lengths of malaria as an impact. And so thinking about how to couple the models onto that kind of decision-making framework has been very valuable. In addition to that, you know, with the Aedes paper, we put all the data out there for people to use. And a group at NCAR approached me and said, hey, you know, we're thinking about this in terms of these, the shared pathways, so the shared socioeconomic pathways, and how that's going to change population vulnerability to these future projections. So how does age structure change with different types of progression and things like that? And sort of who will be, you know, which parts of the population will be at risk. And that's been really fruitful, because that gives, you know, a slightly more nuanced vision of what the future will be and who's going to be vulnerable. And so it's sort of tweaking again what policy decisions could be affected, and who's going to be affected. And so I think there really is a lot of scope for this. I think it is pretty well received. I mean, climate deniers exist.
Yeah. I mean,
I think at the decision table, it also climate change exists. So it's good.
I think building the socio-economic case for the impact that you can deliver, I think is going to be very interesting to see how that unfolds and actually changes the way. I find it very profound, to be absolutely honest, the work that you're doing, because the impact of it's far-reaching, much more than the simple model or the not simple, but the model itself, and I just find it shocking that it's not taken up so quickly by, maybe it's a naive position to take, but they should be listening to you, like, massively.
Oh, thank you.
This is like, so maybe these socio-economic cases and this kind of communication channel is really going to change the way it's perceived, and fingers crossed for that. I'm being told that the system is going
as we know
after you.
As we know, the new IPCC will be coming along soon, and that's sort of a new discussion about how we think about future climate. And so the other part of my work has been a lot about trying to align what we produce with the most recent way people are thinking about climate change. And even within an established framework such as the RCPs, what people think is business as usual has shifted as I've been working on this. And so when we present this, nobody wants to hear me say 2.6 anymore.
Yeah.
That's not what they're making decisions about.
Yeah.
And so, sort of knowing how we move with the times for the climate modeling and how that's been presented to decision makers, sort of coupling this onto it, and then, as you say, bringing in the sort of socioeconomic futures questions, I think that will have its own value.
Yeah.
And I hope people want to work on it.
Formulating the policy trigger, the golden policy trigger, But I mean, I'm being told that our time is coming to an end. I'd like to say thank you very, very much, both of you, for some wonderful answers, taking the time out at this hour to present. I think it's very, very important that we included this session. We'll definitely the whole thing's recorded, we'll edit it and send it back to you so you can use that as an asset in your own rights as well. We will definitely be putting this across social media. All of this is part of our World Dengue Day campaign. We're asking the WHO to ratify a World Dengue Day. There's a 26,000 strong signatories on our change.org. And we've got basically more or less all of the technical community worldwide across different disciplines on a different petition signed. Please help us spread the word for that. And I just want to say again, thank you very, very much for a wonderful presentation. And thanks. And you're getting a lot of thanks from all over the world, actually, from Professor Majid Harandi from Iran, saying thank you very much for your talks. Dr. Ahmed Khater from Egypt, saying thank you very much. Dr. Maripan Tirupati from India, saying thank you very much. Stephen Gramia, the US. Theodore Sai, who I believe is in Indonesia, that's a bit late, saying hi. Rory Gibb, Satish, there's a whole list of them, everybody saying thank you. So I think on that note, thanks a lot, and round of applause, and good evening to you all. Yeah, take care. Bye-bye. Bye.
Thanks a lot. Bye-bye.
Bye-bye. Bye-bye.